So from the previous problem on number 61, we've ended up with the ranking being D, followed by B and E, followed by F, followed by A, and then since C had no torque, it was the last one. So I'd like to continue on and now look at a next problem that involves sort of a unique way of doing torque, which is problem 63. So if you look at page 63, we'll go through the process of drawing this and showing exactly what it looks like. So on page 63, what we have is a mobile. So it's kind of interesting how they design mobile devices. And so that's one of the things that we'd like to look at briefly in this particular problem is the process that they go through to do mobile devices. And so in this one, you'll see that we got this ceiling from which we're supporting this mobile device. And the mobile device is set up so that on this top bar, this is like 1/3 of the length of the bar, and from the pivot, another 2/3. So the string acts as the pivot for this particular one. If we work on the right side, then we have another string that goes down to another bar, in which this is again roughly, this is 1/3 the length, and this is 2/3 of the length. And then from this side, we're going to suspend a rectangular object, which is called D. And from the other side, we're going to have a string that goes down to another bar, except in this bar, it's pivoted in the middle, so one side's half a length, the other side's half a length. And on one side, we're going to hang a heart-shaped object, which is called E. And on the other side, we're going to hang a star-shaped object, which we're calling F. My stars aren't very pretty, but so that's the mobile device on the right side. On the left side, we're going to go down here and we're going to hang, again, a string, and we're going to go to a pivot, and that pivot's going to be a half a length on this side and a half a length on this side, so it's pivoted in the middle. And on the right side, we're going to set up a trapezoidal figure C. And on the left side, we're going to go to another crossbar, in which, again, each one of these is roughly a half of a length based upon the information given. And on the left side, we're going to suspend a rectangular object, and on the right side, we're going to suspend a triangular object. So our mobile device looks kind of cute. It's got different shape objects, and it's balanced. And when we say things are balanced, what we're really saying as far as torque is concerned is that the net torque acting on this object is 0. And if we think of the primary axis of rotation as being this primary place support, then this is our primary axis of rotation. And when we say that the net torque is 0, that means that everything on the right side, if you look at this, is going to tend to cause the object to rotate clockwise, and everything on the left side is going to tend to cause, around this axis of rotation, everything to rotate counterclockwise. And so when we say net torque, we're really saying that all the counterclockwise torques, which are positive, and if we add the clockwise torques, which are negative, then that adds up to be 0. So in essence, you're saying that we want all the counterclockwise torques to be equal to the clockwise torques. Okay? And so to analyze this and to find out which one, because what we wants us to do is rank what are the masses of these objects. I mean, to get this to balance, that means that each one of these objects has a different mass, probably. Otherwise, we won't get it to balance out. So we're going to start with the right side, or the so-called clockwise torques, and then analyze those. And we'll start off, usually you do at the lowest layer. So in this layer, we can say that the torque, if we look at E and F, E sets up a counterclockwise torque around this pivot here, and F sets up a clockwise torque. So my counterclockwise torque for E is going to be this distance, 1/2 the length of that rod, times the gravitational force, which is the mass of E times G. And the angles, all these are right angles for every one of these. And the so-called clockwise torque is going to be the distance R. So again, this is R, and these are F's. The distance R, 1/2 L, and then the gravitational force of mass F, which would look something like this. Notice that the G's divide out, the 1/2 L's divide out, and that just tells me that the mass of E is equal to the mass of F. Which you could have guessed this without having to go through all this long analysis. But again, this is a systematic way in which we could do that. Then if we move up to the next layer, then we can say, well, now D is 1/3 of the distance away from the so-called pivot, which is this axis of support here, and 2/3 of the way from this. So we could set up this same kind of relationship. So we want to remember that. So again, we're going back to counterclockwise torques equal to clockwise torques. So now my counterclockwise torque is going to be 1/3 L times the force of the gravitational force on D, which will be the mass of D times G. And on the other side, we're going to have 2/3 of L, because it's 2/3 of the length. And since it's supporting both of these, we'll have to add up the both masses together. So I'm going to just call that 2 times mass E, since mass F and E are the same, times G. And the G's divide out, the L's divide out, the thirds divide out, and you're left with mass of D is equal to 2 times 2 ME, or 4 times the mass of E. And again, you could have possibly looked at this and came up with that same relationship. So that takes care of my left-hand side. So we're now going to go over to the right-hand side, do the same thing. So we'll start at the bottom layer, and we have that A and B, and so we'll set up our counterclockwise torques equal to our clockwise torques. And so our torque on A is going to be 1/2 the length, because that's the distance it's away from the pivot here, and times the gravitational force of A, which is the mass of A times G. And on the right-hand side, we have 1/2 of L times its gravitational force, which is the mass of B times G. And again, all these divide out, and what we get is that mass of A is equal to the mass of B, which, again, by looking at it, you probably would have guessed that as well. Going to the next layer, we can see that these are halves, and so just by looking at it, you would guess that the mass of C is going to be equal to the sum of the masses over here. So mass of C is going to be twice the mass of A, for instance. But to prove that, we'll go again through our torque analysis. So this side over here is 1/2 L. That's the counterclockwise side. And then because we have these two masses together, it'll be 2 times, let's say, mass of A times G. And on the clockwise side, that's just going to be 1/2 of L times the mass of C, G. So the G's divide out, the half of L's divide out, and so we get that the mass of C is twice the mass of A, which again, we probably would have guessed. And so that gives us the left and right-hand side. So now we can equate the two sides because they're balanced. So we go up to the very top bar, and we would say that everything on the left-hand side, so now we got the counterclockwise torques equal to the clockwise torques. So we have a distance of 1/3 of L, and times the total mass. So we got mass A, mass B, mass C. So mass A are 1 MA each, and mass of C is 2 MA each. So that's a total of 4 MA. On the right-hand side, we have 2/3 of L times G, by the way. And then if we add all these masses together, E and F are the same. D is 4 times that, so that's a total of 6 ME times G. Again, the G's divide out, the L's divide out, the thirds divide out, and I get 4 mass of A is equal to 12 mass of E. So the mass of A is 3 times the mass of E. Well, once I know that, then now I can look at all of these and I can put together the ranking. Because if we start off, the smallest masses seem to be, based upon this analysis here, E and F. And then, so we can go through and set up something. I'm going to do it up here because I ran out of room. So we have mass of E and F are the same. And then we have that the mass of A and the mass of B are the same, but they're 3 times the mass of E, based upon our last statement. And we know that the mass of D is 4 times the mass of E. And then finally, we know that the mass of C, which is twice the mass of A, but mass of A is 3 mass of E, so it must be 6 times the mass of E. So our ranking should be C, followed by D, followed by AB, and then followed by EF. And so that would be our ranking for this particular problem.